Hello everyone. Welcome back to my course Fundamentals of Thermodynamics, Essential Knowledge for Engineers. In this video, we will talk about understanding thrust, the power behind flight. Also, I will be thankful if you give me feedback about this course to make it better and more useful for you. Please write down your thoughts in the comment section or reach out to me via the email provided in my profile. What is thrust? Thrust is the force that propels an aircraft through the air, and it is generated by the aircraft's engines. But how exactly is thrust produced? Fundamentally, thrust is a mechanical force created through the reaction of accelerating a mass of gas. The engine expels the gas toward the rear, and as a result of Newton's third law, the engine and the aircraft are pushed in the opposite direction. To accelerate the gas, a propulsion system is required. While the details of various propulsion systems will be covered later, for now, it is sufficient to think of the propulsion system as a machine designed to accelerate a gas. General thrust equation. From Newton's second law of motion, force can be defined as the rate of change of momentum with respect to time. Momentum is the product of an object's mass and its velocity. Mathematically, the force F over a time interval from t1 to t2 can be expressed as force equals the momentum at the ending time minus the momentum at the starting time divided by the time interval. If the mass remains constant and only the velocity changes over time, this simplifies to the familiar equation. Force equals mass multiplied by acceleration, F equals m times a, where a is acceleration. Tracking mass is straightforward when dealing with a solid because the molecules are tightly bound and retain the solid's shape. However, in fluids, particularly moving fluids such as air or fuel, tracking mass is more complex. In this context, the key parameter is the mass flow rate, which measures how much mass passes through a given area over a period of time. The mass flow rate has dimensions of mass per unit time, such as kilograms per second, and is calculated as the product of the fluid's density ρ, velocity v, and the cross-sectional area A, through which it flows. This parameter is often represented as m dot in aerodynamics. Importantly, refers to the mass flow rate, not the total mass of the fluid. Mass flow rate equals fluid density times fluid velocity times flow area. Because the mass flow rate already incorporates time dependence, the force generated by a propulsion device can be expressed as the change in momentum, which is the difference between the product of mass flow rate and velocity at the exit of the device, station E, and at the free stream or entrance, station 0. Thrust equals mass flow rate at the exit multiplied by exit velocity minus mass flow rate at the entrance multiplied by entrance velocity. Checking the units confirms that mass flow rate times velocity has the correct dimensions of force. An additional factor must be considered if the exit pressure PE differs from the free stream pressure P0. Fluid pressure arises from the momentum of gas molecules and acts perpendicular to surfaces it contacts. Any net change in pressure contributes an additional force across the exit area, AE, given by the difference between exit and free stream pressure times the exit area. Therefore, the most general form of the thrust equation becomes thrust equals mass flow rate at exit times exit velocity minus mass flow rate at entrance times entrance velocity plus exit area times exit pressure minus free stream pressure. In practice, the pressure area term is usually small compared to the momentum terms. Jet engine nozzles are typically designed so that the exit pressure matches the free stream pressure, making the pressure term negligible. In such cases, the thrust simplifies to the product of mass flow rate and velocity difference between the exit and free stream. Since the exit mass flow rate is almost equal to the free stream mass flow rate, it is often convenient to refer to this as the engine airflow rate. Examining the thrust equation reveals two primary ways to generate high thrust. One method is to maximize the engine airflow rate. As long as the exit velocity is greater than the incoming velocity, a high airflow produces high thrust. This principle is the foundation for propeller-driven aircraft and high-bypass turbofan engines, which process a large amount of air each second without significantly increasing its velocity. The other approach is to accelerate a moderate amount of airflow to very high exit velocities, which is the principle behind turbojets and turbojets with afterburners. While extremely high exit velocities can produce large thrust, they also introduce additional physical effects that can impact engine efficiency, which are discussed in detail elsewhere. In rocket engines, the situation is slightly different. Because rockets carry both fuel and oxidizer on board, the free stream mass flow rate is zero. Therefore, the thrust is entirely determined by the product of the exit mass flow rate and exit velocity. For gas turbine engines, the dependence on engine airflow can be expressed through a more practical parameter called specific thrust. For both rockets and turbojets, the nozzle plays two critical roles. It determines the exit velocity based on pressure and temperature conditions, and it regulates the mass flow rate through the propulsion system due to flow choking at the nozzle throat. Consequently, the nozzle design directly determines the overall thrust produced by the engine. Let's go step by step and learn about thrust in different engines. Rocket thrust. On this slide, we present a schematic of a liquid rocket engine. Rocket engines became widely used on several high-speed aircraft after World War II. In a rocket, both the fuel and the oxidizer are stored on board and pumped into a combustion chamber. Inside this chamber, the fuel and oxidizer mix and undergo combustion, releasing a large amount of energy. The resulting hot exhaust gases are then directed through a nozzle, which accelerates the flow to very high speeds. The exit velocity of the gases is determined primarily by the shape of the rocket nozzle, and this velocity is typically supersonic. The exit pressure of the exhaust is also controlled by the nozzle geometry, and it will only match the free stream pressure under specific design conditions. Because of this, it is necessary to use the full version of the thrust equation to accurately describe the thrust produced by the rocket engine. If the mass flow rate is denoted by m dot, the exit velocity by Ve, the exit pressure by Pe, the free stream pressure by P0, and the nozzle exit area by Ae, then the thrust F is given by thrust equals the mass flow rate through the engine, multiplied by the exit velocity, plus the nozzle exit area multiplied by the difference between exit pressure and free stream pressure. This thrust equation applies to both liquid and solid rocket engines. The mass flow rate through the propulsion system is determined by the nozzle design, which controls how much exhaust mass is expelled per second. Rocket designers can study the effects of nozzle shape and operation using interactive nozzle simulator programs that run in a browser, allowing them to visualize how changes in geometry affect exit velocity and thrust. It is important to note that there is no term for free stream mass multiplied by free stream velocity in this equation. This is because rockets do not rely on external air for combustion. The oxidizer is carried on board. As a result, rockets can produce thrust even in a vacuum, where there is no surrounding air. This is in contrast to gas turbine engines and propellers, which depend on the atmosphere to supply oxygen for combustion and therefore cannot operate in space. Turbojet thrust. Most modern passenger and military aircraft are powered by gas turbine engines, also known as jet engines. The simplest type of gas turbine is the turbojet. A turbojet works by continuously drawing large amounts of surrounding air into the engine inlet. At the rear of the inlet, the air enters the compressor. The compressor functions like multiple rows of airfoils, each producing a small increase in pressure. To operate the compressor, energy must be supplied to turn it. By the time the air exits the compressor, it is at a much higher pressure than the free stream. In the burner, a small amount of fuel is added to the high-pressure air and ignited. Although the fuel quantity is small compared to the air, it significantly increases the energy of the flow. The hot exhaust then passes through the turbine, which works like a windmill in reverse. Instead of using energy to move air, the turbine extracts energy from the flow to spin the blades. This energy is used to drive the compressor via the central shaft. After the turbine, the flow still has a higher pressure and temperature than the free stream and is then accelerated through the nozzle. Since the exit velocity is greater than the free stream velocity, thrust is produced. In a turbojet, the exit mass flow is nearly equal to the free stream mass flow because very little fuel is added. The nozzle usually ensures the exhaust pressure returns to free stream pressure. The thrust equation for a turbojet with the pressure area term set to 0 is given by thrust equals the mass flow rate at the exit times the velocity at the exit minus the mass flow rate at the free stream times the velocity at the free stream. This equation has two terms. The first term is called the gross thrust and is associated with conditions in the nozzle. The second term is called the ram drag and is usually associated with conditions in the inlet. The net thrust of the engine is defined as the difference between these two quantities. Net thrust equals gross thrust minus ram drag. Afterburning jet thrust. To move an airplane through the air, a propulsion system must generate thrust. Most modern fighter aircraft achieve this using afterburners on either low bypass turbofans or turbojets. In this section, we will explore the fundamental concepts behind an afterburning turbojet and how it enables high-speed flight. Fighter planes that fly faster than the speed of sound, or supersonic flight, must overcome a sharp increase in drag that occurs near the speed of sound. One effective way to generate the additional thrust required to overcome this drag is by equipping a core turbojet with an afterburner. In a standard turbojet, a portion of the energy in the exhaust gases from the combustion chamber is used to turn the turbine, which drives the compressor. An afterburner supplements this by injecting fuel directly into the hot exhaust stream. In the accompanying diagram, the turbojet nozzle has been extended and includes a ring of flame holders, highlighted in yellow. When the afterburner is activated, additional fuel passes through these rings into the already hot exhaust. The fuel ignites and produces extra thrust. However, it is important to note that combustion in the afterburner is less efficient than in the main combustion chamber of the turbojet. While the afterburner significantly increases thrust, it also consumes much more fuel. The increase in exhaust temperature caused by the afterburner requires a larger nozzle flow area to maintain the same mass flow rate of exhaust gases. This is why afterburning nozzles are designed with variable geometry. They are more complex and heavier than the simple nozzles used on basic turbojets. When the afterburner is turned off, the engine operates like a conventional turbojet without the additional thrust boost. Typically, the nozzle of a turbojet is designed to bring the exhaust pressure back down to match the free stream pressure. The thrust produced by an afterburning turbojet can be described by the general thrust equation, with the pressure area term set to 0. If we denote the free stream conditions with a subscript 0 and the exit conditions with a subscript E, the net thrust F of the engine is calculated as the difference between the mass flow rate times velocity at the exit and the mass flow rate times velocity in the free stream. The thrust is calculated as the mass flow rate of the exhaust multiplied by the velocity of the exhaust at the nozzle exit, minus the mass flow rate of the incoming air multiplied by the free stream velocity. This equation consists of two components. The first term, the mass flow rate of the exhaust times the exit velocity, is known as gross thrust and is primarily associated with the conditions at the nozzle exit. The second term, the mass flow rate of incoming air times the free stream velocity, is called ram drag, which is largely influenced by conditions at the engine inlet. The net thrust of the engine is therefore the gross thrust minus the ram drag. Afterburners are primarily used on military fighter jets and the supersonic airliner Concorde. In the case of Concorde, the afterburners were turned off once the aircraft reached cruise speed to conserve fuel, as leaving them on would have caused the plane to exhaust its fuel supply before completing the transatlantic journey. Despite consuming more fuel, afterburners provide a relatively simple mechanical method to increase thrust and are employed on both turbojets and turbofans. Turbofan thrust. Most modern airliners use turbofan engines because they provide high thrust while maintaining good fuel efficiency. In this section, we will go over the fundamentals of turbofan engines and how they operate. A turbofan engine is an advanced version of the basic gas turbine engine. Like all gas turbines, it has a core engine, which includes the compressor, combustion chamber, and turbine. In a turbofan, this core is surrounded by a large fan at the front and an additional turbine at the rear. Both the fan and the fan turbine have multiple blades similar to the core compressor and core turbine, and are connected by an additional shaft. Some of these blades rotate with the shaft, while others remain stationary, just like in the core engine. The fan shaft passes through the core shaft for mechanical reasons, forming a two-spool arrangement, one spool for the fan and one spool for the core. Some advanced engines include more than two spools, which allows certain sections of the compressor to operate more efficiently. The operation of a turbofan begins with incoming air being captured by the engine inlet. A portion of this air passes through the fan and continues into the core compressor, and then the combustion chamber, where it is mixed with fuel and burned. This hot exhaust passes through the core and fan turbines and then exits the nozzle, much like a conventional turbojet. This portion of the airflow is called the core airflow and is denoted as mass flow of the core. The remaining air bypasses the core, traveling around it instead of through the combustion chamber. This bypassed air passes through the fan, which increases its velocity slightly above the free stream speed, similar to the action of a propeller. This airflow is called the fan flow or bypass flow and is denoted as mass flow of the fan. The ratio of the fan mass flow to the core mass flow is called the bypass ratio. The total mass flow through the engine inlet is the sum of the core and fan flows. This can be expressed as total incoming mass flow equals the mass flow through the fan plus the mass flow through the core. A turbofan generates thrust from both the core and the fan. If we label the exit of the core as station E, the exit of the fan as station F, and the free stream as station 0, the total thrust can be calculated by summing the contributions from each stream. Thrust equals the mass flow through the fan multiplied by the fan exit velocity, minus the mass flow through the fan times the free stream velocity, plus the mass flow through the core multiplied by the core exit velocity, minus the mass flow through the core times the free stream velocity. By combining terms and using the definition of the bypass ratio, the total thrust can also be expressed as thrust equals the core mass flow multiplied by the core exit velocity, plus the bypass ratio times the core mass flow multiplied by the fan exit velocity, minus the total mass flow multiplied by the free stream velocity. Since the core fuel flow is only slightly affected by the addition of the fan, a turbofan produces significantly more thrust for nearly the same fuel consumption as a basic core engine. This makes turbofans very fuel efficient. High bypass ratio turbofans can approach the fuel efficiency of turboprops. Because the fan is enclosed in the engine inlet and consists of multiple blades, it can operate efficiently at higher speeds than a simple propeller, making turbofans ideal for high-speed aircraft. Conversely, propellers are used for lower-speed aircraft because they are less efficient at high speeds. Even low bypass ratio turbofans are more fuel efficient than basic turbojets. Many modern fighter aircraft use low bypass ratio turbofans equipped with afterburners. These engines allow the aircraft to cruise efficiently while still providing high thrust for combat maneuvers. Although fighter planes can fly faster than the speed of sound, the air entering the engine must remain below supersonic speeds for optimal efficiency. Therefore, the engine inlet is designed to slow down the incoming air from supersonic speeds to subsonic speeds before it reaches the fan and core. Turboprop thrust. Many low-speed transport aircraft and small commuter planes use turboprop engines. The turboprop combines a gas turbine core with a propeller to generate thrust. Propellers develop thrust by moving a large mass of air with a relatively small change in velocity. This makes them very efficient, and they can be driven by almost any kind of engine, even humans. In a turboprop, the gas turbine core is used to turn the propeller. A turboprop propulsion system has two main parts, the core engine and the propeller. The core engine is similar to a basic turbojet, with a compressor, burner, and turbine. At the exit of the main turbine, the hot exhaust passes through an additional turbine, which is connected to a drive shaft. This shaft passes through the core shaft and is linked to a gearbox that drives the propeller. Most of the energy from the exhaust is used to turn this additional turbine, so the exhaust velocity of the core is relatively low and contributes little to overall thrust. The propeller produces the majority of the thrust. The thrust of a turboprop is the sum of the thrust from the propeller and the core. Using the basic thrust equation for each component, we can write the net thrust is equal to the mass flow rate in the free stream multiplied by the velocity at the exit of the propeller minus the mass flow rate in the free stream multiplied by the free stream velocity plus the mass flow rate exiting the core multiplied by the exit velocity of the core minus the mass flow rate entering the core multiplied by the velocity into the core. Here, the free stream conditions are denoted by 0, the exit of the propeller by 1, the exit of the core by E, and the entrance to the core by C. The mass flow rates are m0, mc, and me, and the velocities are v0, v1, and ve. Since the mass flow through the propeller, m0, is much greater than the mass flow through the core, mc, and the core exhaust velocity, ve, is low and nearly equal to the velocity into the core v1, while the mass flow exiting the core, me, is almost equal to mc, we can simplify the thrust equation. The net thrust is approximately equal to the mass flow rate through the propeller multiplied by the change in velocity across the propeller, plus the mass flow rate through the core multiplied by the change in velocity through the core. The first term, corresponding to the propeller, is much larger than the second term from the core. This matches pure propeller theory. Thrust is primarily generated by the mass flow through the propeller multiplied by the change in velocity across it, with a smaller contribution from the core exhaust. Because propellers become less efficient at high speeds, turboprops are mainly used for low-speed aircraft, such as cargo planes. High-speed aircraft typically use high bypass turbofans, which offer both higher speed capability and fuel efficiency. A variation of the turboprop is the turboshaft engine. In a turboshaft, the gearbox drives another device instead of a propeller. Turboshaft engines are commonly used in helicopters, as well as in tanks, boats, and even some race cars in the late 1960s. Propeller thrust. Most general aviation or private airplanes are powered by propellers. While the details of how a propeller generates thrust are quite complex, we can still understand some of the fundamentals using a simplified momentum theory. On the slide, we show a schematic of a propeller propulsion system at the top and some of the equations that define how a propeller produces thrust at the bottom. The details of propeller propulsion are very complex because the propeller is like a rotating wing. Propellers usually have between 2 and 6 blades. The blades are usually long and thin, and a cut through the blade perpendicular to the long dimension will give an airfoil shape. Because the blades rotate, the tip moves faster than the hub. To make the propeller efficient, the blades are usually twisted. The angle of attack of the airfoils at the tip is lower than at the hub, because it is moving at a higher velocity than the hub. Of course, these variations make analyzing the airflow through the propeller a very difficult task. Leaving the details to the aerodynamicists, let us assume that the spinning propeller acts like a disc through which the surrounding air passes, the yellow ellipse in the schematic. The engine, shown in white, turns the propeller and does work on the airflow, creating an abrupt change in pressure across the propeller disc. This change in pressure, often referred to as a pressure jump, is mathematically denoted by the Greek symbol delta P. The propeller behaves like a rotating wing, and similar to airfoil theory, the pressure over the top surface of a lifting wing is lower than the pressure below it. For a spinning propeller, this means that the pressure in front of the propeller disc is lower than the free stream pressure, while the pressure immediately behind the disc is higher than the free stream pressure. Downstream of the propeller, the airflow gradually returns to free stream conditions as the pressure equalizes, but the velocity of the air at the exit is higher than the free stream because the propeller imparts energy to the airflow through the engine's work. Bernoulli's equation can be applied to the air in front of the propeller disc and to the air behind it, but it cannot be applied across the propeller disc itself because the assumptions underlying Bernoulli's equation are violated by the work done by the engine on the air. In summary, the propeller acts both as a rotating lifting surface and as a device that accelerates air, creating a localized pressure difference across its disk. This pressure difference drives the increase in air velocity downstream, which is the fundamental mechanism through which the engine generates thrust. From the basic thrust equation, we know that thrust depends on the mass flow rate through the propeller and the change in velocity of the air. Denoting free stream conditions with subscript 0, propeller conditions with subscript P, and exit conditions with subscript E, the thrust is thrust equals the mass flow rate through the propeller multiplied by the exit velocity minus the mass flow rate through the propeller multiplied by the free stream velocity. Since the exit pressure equals the free stream pressure, there is no pressure area term in this case. The mass flow rate through the system is constant, and at the plane of the propeller, it can be expressed as the product of air density ρ, the velocity through the propeller Vp, and the area swept by the propeller A. Mass flow rate equals the air density multiplied by the velocity through the propeller multiplied by the area of the propeller disk. Substituting this expression into the thrust equation gives the thrust in terms of the exit velocity, entrance velocity, and propeller plane velocity. Thrust equals the air density multiplied by the velocity through the propeller multiplied by the area of the propeller disk multiplied by the difference between exit velocity and free stream velocity. Using Bernoulli's equation, the total pressure ahead of the propeller disk is total pressure equals the static free stream pressure plus 1/2 times the air density multiplied by the square of the free stream velocity. Downstream of the disk, the total pressure becomes total pressure equals the static free stream pressure plus 1/2 times the air density multiplied by the square of the exit velocity. Thus, the pressure jump across the propeller disk is pressure jump equals the total pressure downstream minus the total pressure upstream. Or, substituting the Bernoulli expressions. Pressure jump equals 1/2 times the air density multiplied by the difference between the square of the exit velocity and the square of the free stream velocity. The force on the propeller disk is equal to the change in pressure multiplied by the area. Substituting delta P gives force equals 1/2 times the air density multiplied by the area of the propeller disk multiplied by the difference between the square of the exit velocity and the square of the free stream velocity. Combining this with the previous expression for thrust and solving for the velocity through the propeller disk, we find velocity through the propeller disk equals 1/2 the sum of the exit velocity and the free stream velocity. This shows that the airspeed through the propeller disk is simply the average of the free stream and exit velocities. It is important to note that this thrust calculation represents an ideal value and does not account for losses such as tip losses or other high-speed effects. These losses require a more detailed propeller theory, which can also predict the magnitude of the pressure jump for a given geometry. Nonetheless, the simple momentum theory provides a solid first approximation that can be used for preliminary propeller design. Ramjet thrust. A ramjet engine is a very simple and lightweight propulsion system designed for high-speed flight. Unlike a turbojet engine, a ramjet does not have any moving parts. Its structure is composed only of an inlet, a combustor, which includes a fuel injector and a flame holder and a nozzle. This simplicity makes it mechanically reliable, but it also means that the ramjet relies entirely on the forward motion of the aircraft to operate efficiently. The operation of a ramjet begins with the continuous intake of large volumes of air from the surroundings. As the aircraft moves forward, air enters the engine inlet at high speed. This air is slowed down as it passes through the inlet, and its kinetic energy, related to velocity, is converted into increased static pressure. By the time the air exits the inlet, it is at a significantly higher pressure than the free stream air outside the engine. Interestingly, even though the free stream velocity can be subsonic or supersonic, the flow leaving the inlet of a ramjet is always subsonic, ensuring stable combustion in the burner. Inside the burner, a small amount of fuel is injected and mixed with the incoming high-pressure air where it is ignited. In typical ramjet operation, for example, 100 pounds of air per second might be combined with only 2 pounds of fuel per second. This illustrates that most of the energy in the exhaust comes from the surrounding air rather than the fuel itself. Flame holders in the burner help localize the combustion process, stabilizing the flame and ensuring the burning occurs subsonically. Once combustion is complete, the hot exhaust gases pass through a nozzle, which is carefully shaped to accelerate the flow. As the gases exit the nozzle at a velocity higher than the free stream air, thrust is generated. Because only a small amount of fuel is added to the flow, the mass flow rate at the exit of the engine is nearly equal to the free stream mass flow. The thrust produced by a ramjet can be understood through the thrust equation, which consists of three components: gross thrust, ram drag, and a pressure correction. Denoting the free stream conditions with the subscript 0 and the exit conditions with the subscript E, the thrust F is calculated as the thrust F of a ramjet is equal to the mass flow at the exit multiplied by the exit velocity minus the free stream mass flow multiplied by the free stream velocity plus the difference between the exit pressure and the free stream pressure multiplied by the nozzle exit area. In this equation, the first term, the mass flow at the exit multiplied by the exit velocity, is known as the gross thrust. This term primarily depends on the conditions in the nozzle. The second term, the free stream mass flow multiplied by the free stream velocity, is called the ram drag, which represents the aerodynamic resistance caused by the incoming air. In a ramjet, the exit velocity is supersonic, and the exit pressure is influenced by the ratio between the nozzle throat area, the narrowest part of the nozzle, and the nozzle exit area. Only under a specific design condition will the exit pressure match the free stream static pressure. For all other operating conditions, the third term, which accounts for the difference between exit pressure and free stream pressure multiplied by the exit area, must be included. This pressure correction is usually small compared to the gross thrust, but is considered for completeness in calculations. Overall, the simplicity of the ramjet, combined with its ability to use high-speed airflow efficiently, makes it ideal for certain high-speed applications, despite the fact that it cannot operate at low speeds without external assistance. Okay guys, now let's have a little quiz. The quiz consists of 5 questions. I'll give you 10 seconds for each one, and then I'll show you the correct answer. Let's start with the first question. Question 1. Which of the following statements correctly describes why turboprops are more efficient at low speeds than high speeds? The correct answer is propellers move a large mass of air with a small change in velocity, which is efficient at low speeds. Question 2. In a turboprop engine, where does the most of the thrust come from? The correct answer is the propeller. Question 3. Which of the following is true about propeller thrust according to momentum theory? The correct answer is the propeller acts like a rotating wing, creating a pressure difference that accelerates air. Question 4. Why can a ramjet engine not operate efficiently at low speeds? The correct answer is it lacks moving parts to compress incoming air, relying on high-speed forward motion to generate pressure. Question 5. For a ramjet engine, which term in the thrust equation represents the aerodynamic resistance caused by incoming air? The correct answer is ram drag. Unlock the world of aerospace engineering with my other expertly designed courses. In Aerospace Engineering, Basics of Aviation Engines, you'll explore the different types of aerospace engines and how they perform, giving you a strong foundation in the propulsion systems that power modern aircraft. Then, take your knowledge to new heights with Aerospace Engineering, Aerodynamics and Structures, where you'll dive into the design and performance of aerospace structures and their aerodynamic behavior. Finally, expand your expertise with aerospace engineering, avionics, and aerospace systems, where you'll learn about the critical electronic systems that control and monitor modern aircraft, bridging the gap between engines, structures, and flight systems. Whether you're a student, aspiring engineer, or aviation enthusiast, these courses will equip you with essential knowledge to understand and contribute to the future of aviation. Join hundreds of learners and start building your aerospace journey today. Thank you guys for watching this video. If you have any questions about this lesson, feel free to ask me in the comment section. I will answer as soon as possible. We can continue to the next lesson and learn about the Carnot, Otto, and Brayton cycles. See you in the next video. Bye.